Needs very little introduction, so I'll be brief. Jim, of course, a professor here. Before that, he was an undergrad at Whitman College in Walla Walla, Washington, a city that, along with Kalamazoo, I'm still trying to convince my non-American wife is real. And then went to Cornell for graduate school. We got his PhD in 2014, working with Don Lai. Then came here as a DeBridge postdoctoral fellow, where he worked on a number of projects and also spent a lot of time, as he still does, collaborating with colleagues at KITP, and clearly impressed many of us, so much so that we hired him in 2016 and started in 2017 as an assistant professor on the faculty here. And since then, he's done a lot of work and built a lot of collaborations with many people here, many of the folks in this room, many of the students here who've been mentored by him or go to his group meetings, or collaborated with him. He's won a Sloan Award and a Roseville Innovation Award, and he's worked on a broad variety of topics. We sort of have a running semi-joke of trying to figure out how to explain what Jim works on versus what I work on versus what other people work on when we do our introductions at the coffees, and I think your latest suggestion was size scale barrier, but I think that still does a disservice to the broad range of topics related to stars and stellar evolution, planets, seismology of both planetary bodies and stars, binaries of white dwarfs and other compact objects, sources for LIGO, and many other topics that Jim has worked on. And also brings a very different approach. I think Jim, along with Sterl, is trying to counterbalance our whole hallway with folks like myself and Saul and Mark and Katerina, who just want to solve everything on a computer, and he insists that we still have actual equations from time to time. So, without further ado, I look forward to hearing more from Jim and also seeing what this is about.
Yeah. Thank you, Phil. Thank you, everybody, for coming. It's a pleasure to be here. I don't think any of you heard a word Phil said because you were transfixed by this colorful bowl of mysterious liquid. So it's a little hard to explain what I do sometimes, but I'd say most of what I work on is astrophysical fluid dynamics. So there can be many contexts. It can be stars, it can be planets, it can be supernovae, all kinds of things. The common theme that I'll be talking about today is basically waves that propagate inside of fluids like stars or planets. I'm also teaching fluid dynamics this quarter, so I thought I'd set up a little demonstration that I demoed in my class yesterday. So what we have here is a bowl of 3 different fluids, blue, yellow, and red. And what you can see is that they separate out because the red fluid is the lightest, the blue fluid is densest, so they sink. Now, when you have interfaces like this, when you have a density gradient between the fluids, you can have waves that propagate along those interfaces. So we're going to try to excite some of those waves here. So you can see, especially on the bottom, we get these nice big fluid waves. Even though the top of the fluid is basically not moving at all, we get these nice undulations that propagate on these interfaces. And they're very slow, gentle, side-to-side motions. These are the same kinds of motions associated with gravity waves that propagate inside of planets and stars. So the restoring force is buoyancy, right? If I try to displace a denser fluid below a lighter fluid below a denser fluid, then it gets pushed back by the buoyancy force, and so we excite a wave. So in this case, we have alcohol on the top, oil in the middle, and water on the bottom, and we can get all kinds of waves. There are these very low frequency motions. So we're going to see these coming up in all areas of astrophysics, and these waves can both affect the objects we're looking at and also tell us a lot about them. You can also get higher frequency waves. So there's also basically a surface wave associated with the whole thing, which if I shake the whole thing a little bit, we see now basically everything moves coherently. So that's a higher frequency oscillation. Basically the whole thing rocks back and forth. So we can think of that as a fundamental mode of the system, whereas these lower frequency motions, these internal waves, are going to be mostly what we're focusing on today. So you can come up and look at this afterwards if you want. So I'll get to the science now. Okay, So, fluid dynamics in many contexts, especially these buoyancy waves. This is some snapshots of what they look like in something like the sun. So the sun, the outer layers are convective, but the inner layers are stably stratified. It has a continuous density gradient that supports a continuum of waves that you see propagating here. So these gravity waves. So I've been blessed to work with a big group over the last several years. We've worked on many different topics, so I can't cover everybody's research. But I'm going to cover a few themes, starting with our own solar system. We're going to go all the way from this bowl of liquid here all the way up to energetic supernova if we get time in this talk. I'm going to start with the planet Saturn. And here we have a big unsolved problem, which is what is the internal structure of giant planets? We don't really know what giant planets look like on the inside. It's very difficult to make any kind of measurement that tells us precisely what's there. Now, the way we know about Earth's interior, or the sun's interior, is through seismology. So if we can detect oscillations of planets, we can really learn a lot about their internal structure. And that's what I've been working on with Chris Mankiewicz and Janusz Dewberry, some postdocs here. And the way we actually detect pulsations of Saturn are with its rings. So Saturn has this dense system of rings, and at certain points in the rings, there are actually resonances between the epicyclic frequency of the rings and oscillations of Saturn. And so that excites a wave that propagates through the rings, which we can then measure. We can't see the oscillations of Saturn itself, we can just see their gravitational influence on the rings. And what we can measure from the rings, and this has been done some great work by Matt Hedman and Phil Nicholson, and a few others, is we can measure the pattern number. So in other words, how many arms are in these spiral patterns in the rings. That tells us the azimuthal pattern number of the mode in Saturn. And we can also measure the frequency of that oscillation. So this is a compilation of most of the measurements we have at this point from one of Janusz's papers. So these diamonds here, these are the observed modes that excite waves in the rings. And you can see that most of these diamonds overlap with these blue circles, which are the predicted locations of the fundamental modes of Saturn. So that's this large-scale, coherent side-to-side motion of Saturn, similar to this large-scale motion of the bowl. So that's what most of these modes are. But you can see down here at low wave numbers, there's a few extra modes, like this one and these ones down here. So those can't be explained as F modes. And the only explanation we have for those is that they're gravity modes. They're basically these lower frequency oscillations that are confined to the internal parts of the planet. But we can see their effect on the rings. So we can learn a lot from these modes if we know how to interpret them. And that's what Janusz and Chris and I have worked on. And in particular, one thing that's new that happened just in the last few years is this mode was observed for the first time. And what this mode is, this is one of those internal gravity modes. And also one of these is an internal gravity mode, and that means we have a few of those now. And that's really useful for seismology because now we can start to measure the frequency spacing between those modes. And that's what really gives us a good handle on the internal structure, because that tells us the level of density stratification within the planet. So again, these large-scale modes, these are the F modes. This is what their eigenfunction looks like inside of Saturn, whereas these gravity modes, they're really confined to the internal core of Saturn, which we've learned to be this diffuse, stably stratified core, similar to actually what's in the sun in many respects. There's also these more complicated modes that probably have very complicated structures. These are called rosette modes. They're due to the very rapid rotation of Saturn. So I won't go into them too much, but they're kind of a mix between these rosette modes and these fundamental modes. So how do we actually learn from these? Well, we basically just build a lot of models and see which ones match the data. I think that's the standard practice in astrophysics these days. So this is what Chris has done. So we have built some parameterized models of Saturn where we basically have a convective envelope with uniform composition, and then the metallicity of the material rises from some outer radius towards the core. And we parameterize basically the inner and outer radius of this metallicity gradient. And the fact that we have this composition gradient gives us a density gradient that is the restoring force for these internal gravity waves. So this bottom panel, this is the Brunt-Väisälä frequency of each of these models. And that's really what the G-modes tell us about it. They tell us about this Brunt-Väisälä frequency, which is really measuring the density gradient within Saturn. So if we can measure that period spacing, we basically get some measurement of this Brunt-Väisälä frequency. So the right panel shows the stars are the observed oscillations. Here we're just going to focus on the m equal 2 modes. So these are the observed modes. The blue dots are the predicted modes for each of these models. And what you can see here is that this mode here, this is the highest frequency mode we've observed, this can only be explained by the models that have very light colors. Those are the models where this diffuse core comes way out to more than half of the radius of Saturn. So that tells us that this core of Saturn, actually, it's not a step function. We don't go from a solid rock core to a gaseous envelope. It's a very broad, smooth transition. Otherwise, we would not be able to explain these gravity modes that we see in the core. Now, this work also involved matches to things like the gravity field of Saturn, the J2, the J4, et cetera. So there's really a lot under the hood here. But Chris made many models, and they're colored here basically by their likelihood, how well they match the data. What we can see is that the models that match the data have an outer core radius of something like 60% the radius of Saturn. And the mass, the total mass contained in that stably stratified core, is of the order of 50 or 60 Earth masses. So that's about 60% of the mass of Saturn as well. So in contrast to the standard picture of just a big convective ball, these planets actually have these nice smooth density gradients, very different from the internal structure of the Earth. So that's something, we've also gotten hints of that from many other sources of data, but I think this is really the smoking gun signature that's given us the best constraints on giant planet structures that we have to date. So that's Saturn. Now, these modes of Saturn and the structure of Saturn also has implications for its moons. So Saturn has a very intricate system of moons. Mimas, Enceladus, Tethys, Dione, Rhea, and Titan, its largest moon, is off the plot here. These moons are close enough to Saturn that they experience tides. They raise a tidal bulge on Saturn, and the dissipation of that bulge causes the moons to migrate outwards in the same way that our own moon migrates out from the Earth. Now, the mechanism for that migration is not very clear, but most theories point towards some sort of resonance between the moon's orbits and the oscillations of Saturn. We've learned now that Saturn has this stably stratified core that supports gravity modes. So very similar to the modes that resonate with the rings, there will be slightly lower frequency modes that resonate with the moons. And that means a moon can tidally excite one of those modes. And you can think of each mode as a harmonic oscillator inside of Saturn. Okay, so its amplitude scales like there's some forcing function, and it scales like its frequency divided by the difference between the forcing frequency and the mode's natural frequency. So when the mode's natural frequency is equal to the forcing frequency produced by one of these moons, we get a resonant response. This amplitude becomes large, and that means the energy dissipation, which scales as that amplitude squared, becomes much larger. So you can get very large amounts of dissipation if you force one of these modes at resonance. So that's been known for a long time. What's especially interesting about Saturn, and the work that we've really contributed, is the realization that these modes, they depend on the structure of the planet. So their frequencies are not actually constant. So as an example, here's the tidal migration timescale near one of these resonances with one of Saturn's modes. So we get rapid migration or short migration timescale right at resonance. But you can think about some location just off resonance where the moon migrates outwards on some timescale of order a few gigayears. But the mode location itself is also moving because Saturn's structure is gradually changing. So there's things like helium rain that's occurring in Saturn. So the structure is changing. That means all those mode frequencies are changing. So if those mode frequencies increase in Saturn's frame, that actually means the resonant location moves outwards. And that means you can actually get a resonance lock between the moon's and Saturn's mode. So imagine we have a moon right here. If I displace it inwards, it's going to migrate out faster, and it's going to return back to this equilibrium. If I displace it outwards, it's going to migrate slower, and this whole mode will catch back up to it again. So that process is known as resonance locking. And the consequence of that is we can think of the moons as waiting for one of these resonances to sweep it up, and then it rides this resonance outwards. And so in that scenario, the only thing that determines the moon's migration rate is actually the evolution of this mode frequency, and hence the evolution of the planetary structure. So we can actually tie Saturn's moons to the structure of Saturn and how that's changing. Now, we don't understand that super well, but we think that Saturn is evolving kind of on a time scale of order the age of the solar system, so of order 5 gig years, 10 gig years, something like that. And the migration rates of many of the moons have now been measured. And this is actually something I spoke about several years ago. We now have measurements from Valerie Linnet's group. These are astrometric measurements that have measured the migration timescales of the inner moons. And you can see that they're all about of order 10 gig years, which is what we should expect from this theory. This is very different from if you assume Saturn had some constant quality factor, which is the way people usually parameterize tides, then the migration rate should follow this blue dashed line. So we can see the actual migration timescales are much shorter than what people had thought, and that is the prediction of this resonance locking mechanism. Now, the new thing that's just happened recently is in addition to these moons, we've been able to measure the migration rate of Titan. So actually, I published this resonance locking prediction several years ago, and then after it came out, Valerie Linnet contacted me and he said, I have this measurement, but I never believed it until I saw that your paper predicted this could happen. I said, okay, great, let's write a paper. And then a few months later, Paolo Totora, who's the head of a group in Italy, contacted me and said, we have this measurement of Titan's migration from radio science data on Cassini, and we never believed it until we saw your paper. I said, okay, great. And so we all got together and wrote this paper that includes the migration rate of Titan, which has also been measured to be about 10 gig years. Again, consistent with this basic model. So in this case, we actually have two totally different measurements. One is coming from astrometry, so they're just the long-term positions of the moons. And the other is coming from radio science data from Cassini, which is some very close passages of Titan, so it can measure its position very accurately. And so again, it's pointing to this model of resonance locking, whereas everybody before thought that Titan wouldn't really migrate at all. So I think this resonance locking is the only thing that can actually explain the data that we see. And it has some big implications. For instance, the effective tidal quality factor of Saturn due to Titan is actually extremely low. It's of order 100, so that's a few orders of magnitude lower than people usually thought. And these kinds of effects could happen in totally different systems, like exoplanets or stellar binaries, which I'll talk about next. Another implication for Saturn's system is that the moons have actually migrated in a much different manner than people had assumed in the past. So this generally predicts actually less migration for the inner moons compared to old models, which are these black dashed lines, and much more migration for the outer moons. So that might have all kinds of implications for how the moons formed, how they've evolved, and that's something I've been talking to Constantine and Max about, trying to understand the implications. So as I mentioned, this same process can potentially happen in all kinds of systems. So for instance, exoplanet systems. So exoplanets, especially short-period exoplanets, they might orbit their star in a couple of days, whereas stellar spin periods like the sun, they tend to be much longer than that. So that means the planets orbit much faster than the stars spin, and so typically their orbits decay with time instead of expanding outwards. But you can still have planets that are resonantly exciting oscillations, again, these gravity mode oscillations of the star. The nice thing about stars like the sun, which are typical exoplanet hosts, is that we actually understand their structure and evolution much better than we do for planets like Saturn. So we can actually calculate this resonance locking prediction much more accurately. So here's an example of this tidal migration timescale due to resonances with the sun's gravity modes. So you can't tell, but this is actually a series of very narrow, sharp resonances. If you zoom in, they have a structure very similar to what we saw here. This is just an example of, in this particular model, there's a resonance with a gravity mode at this orbital period. And at that resonance, you get a very short tidal migration timescale. The the orange line is an attempt to account for effects of nonlinear dissipation of these modes, which are much more difficult to calculate and not super well understood. But the basic idea is that for either of these models, these resonant locations are migrating inwards with time. And as long as there's some location where this orange or blue line intersects the black line, which is the time scale on which the moon is migrating, the resonance is moving inwards, then the moon can surf that resonance and migrate inwards on a time scale dictated by the sun's evolution. So in this case, what this plot shows is this just shows the frequency of some of the sun's oscillation modes as a function of time. And so what you can see is that the mode frequencies all increase with time. The reason for that is that as stars like the sun evolve, they fuse hydrogen into helium, and so they get denser and denser at their cores. That means this level of this density gradient goes up, and so the gravity mode frequencies also go up. So what that means is that a moon migrating inwards can get caught into resonance with one of these modes, and it can just follow one of these tracks all the way up. So that's the idea, is that you form a moon out of resonance, but very quickly the star evolves, the resonance catches up with the planet, and then carries it inwards. So again, this theory makes some very unique predictions about the migration rates and the quality factor of the star. So an example is this red line. This is a model for how a planet should evolve if it's caught in one of these resonance locks. And you can see it just predicts this very smooth inward migration on a several gig-year time scale. Now, there can also be other tidal effects, like people have talked about nonlinear damping of tides, tidally excited gravity waves that basically just go right into the core of the star and break. Those models predict very different behavior. So they predict gradual migration, and then they just sort of predict the planet to plunge in. And we think maybe that's what happens for the most massive planets, because those ones excite the mode to such large amplitude that those nonlinear effects become very important. But for the lower mass planets, we think they should migrate in more smoothly. And the prediction is that the tidal quality factor of the star can be very different. So for a low mass planet, it's basically this very low number. For a high mass planet, it's a much higher number, but the migration timescale is actually kind of similar. So there is some observational evidence that points towards this phenomenon. So this is a plot from our paper. All the data here is from a paper by Penev et al. 2018. So they have tried to measure the quality factor of stars based on their spin measurements, based on their spin rates. And so they've used that to try to infer basically the rate at which the star has been tidally spun up, and therefore figure out what this tidal migration rate is, or what the quality factor of the star is. So their data is fit by this yellow dashed line. The prediction from resonance locking is this red solid line, and there's no free parameters in that model. So at first sight, it's a very good match. So it may be good evidence that resonance locking is dictating the tidal migration. In this case, it's interaction between hot Jupiters and their host stars. We're a little bit careful about that interpretation, because you can get the same type of result if these stars are actually young. They haven't actually been tidally spun up yet, and they're just rapidly rotating because they're young. So we talk about that a bit in the paper. But if the age estimates from Penev et al. Are correct, then it's definitely, the measurements strongly agree with the predictions of resonance locking. So we'll have to wait out and see what happens there. But there's definitely a clear prediction from this model that we can test. Okay, so we've done planets, we've done sun-like stars and exoplanets. Now I want to take one step up and go to red giant stars. So red giant stars, like the sun or like Saturn, they have convective envelopes and they have radiative cores. And what that means is that gravity waves can propagate in their cores. And we can actually see these with asteroseismic observations, say space-based photometry like Kepler test photometry of these stars. You just measure the brightness of one of these stars and take a power spectrum, and you see this very regular pattern of modes. And these are actually mixed modes that behave like acoustic waves near the surface. but they behave like gravity waves in the core of the star. And so they have this kind of uniform spacing here. That's called the period spacing of the gravity modes. And that basically tells us the level of stratification in the core of the star. So we can measure that quite accurately. This is a nice plot from Matthew Broward's work, where this measurement has been made for thousands of stars at this point. And so what we do here is we plot that period spacing. So we're plotting this spacing here as a function of there's a different spacing, which is basically the spacing between these central peaks here. Or they've actually cut out the radial modes here. So it's this spacing here, and that's dictated by the acoustic waves in the surface of the star. So that's what the x-axis is. So when you make that measurement for all these stars, you see two very distinctive, clear groups of stars. This big clump up here, these are red clump stars. These are stars burning helium into carbon in their cores. They have radii of about 10 solar radii, mostly 1 to 3 solar mass stars. This branch down here, this is the red giant branch. So these are stars that have exhausted all their hydrogen in the core. They're now burning hydrogen into helium in a shell around the core, and they move from right to left on this plot. They move to smaller period spacing because the core is getting denser and denser and denser. So whenever you get this much beautiful data, as a theorist, you have to start thinking, okay, what can we learn from this? What are the surprises that appear in this data? And one of the surprises is that some of the stars on this plot shouldn't be there. So for instance, you see some of these red points back down here. These are stars whose mass is something like 2.5 solar masses. But their core structure is similar to that. It's even off this track a little, of a much lower mass star. If you actually make models, all these 2 solar mass stars should come in up here. And that's probably what these are. So we actually have a bunch of outliers, stars that shouldn't be there. So whenever you see that in stellar astrophysics, you have to think, okay, what about, well, you can either think about magnetic fields, which is what I talked about 6 years ago, or binaries. Okay, so what we think is that binary interactions are producing a lot of these weird things, and this is work done by Nicholas. So the question is, what is the asteroseismic signature of a star that used to be a binary star that then merged together? Okay, so if you have a 2.5 solar mass star, when it exhausts hydrogen in its core, it makes this roughly 0.3 solar mass helium core, and as it's moving through this part of the HR diagram, its core is still non-degenerate. It's still starting to contract. Whereas if you look at a 1.5 solar mass star, its core has contracted. It's become this degenerate ball of helium in the center. But that should only happen for stars less than about 2 solar masses. Now, if you take a 1.5 solar mass star and have it merge, say with a 1 solar mass companion, then basically this 1 solar mass companion will just add its mass to the envelope of this star. At this point, the core is too dense to really be disturbed. It has a density of 10 to the 4, 10 to the 5. So it won't get disrupted by a merger, and so this mass will just go into the envelope of the star. So you can wind up with a red giant that has the mass of a 2.5 solar mass star, but the core structure of a much lower mass star. So we modeled this with the MESA stellar evolution code, and in particular, what we wanted to calculate was this Brunt-Väisälä frequency, this buoyancy frequency of the core of these stars. So the red dashed line, this is this Brunt-Väisälä frequency for the 2.5 solar mass star. And at the same luminosity or same location on the HR diagram, the blue dashed line is what you'd get for a 1.5 solar mass star. And the green line is what you'd get for that merger model. So you can see that it has an almost identical, its core structure is almost identical to a 1.5 solar mass star, even though it has a total mass of 2.5 solar masses. And again, it's this Brunt-Väisälä frequency. Basically, it's the integral of this line that determines this period spacing that we can observe. So we can predict where these stellar merger remnants should be. So if we, again, look at the same slice of data, these are the red giant branch stars, so let's zoom in on that. What we've highlighted here with these green and yellow stars and diamonds, these are stars that have mass much too large to be in this part of the diagram, but they have about the right core properties to be one of these mergers. So you can see these tracks here on the left. This is where a 2.5 or 2 solar mass star should evolve through. But all these stars, which have asteroseismically measured masses and period spacings, are clearly not lying on top of those tracks. But they are consistent with this salmon dashed line here. This is where merger models should go. And actually, depending on exactly when the merger happens, you can have lines going basically anywhere below this red dashed line here. So these are probably mergers that happen on the red giant branch. These are probably mergers that happened kind of near the end of the main sequence. So I should also say, we think that these are merger remnants. Another possibility is that some of these things are actually in binary systems where the mass they've accreted stably. So it didn't have to necessarily be 2 stars that merged. It could be that there was a companion star which donated a bunch of mass. And so that theory can be tested by radial velocity monitoring of these stars. And we can also do things like try to look for other activities at this, other indicators that this was a merger, like see if they have rapid rotation or enhanced lithium or X-ray activity, those kinds of things. So we've looked through some catalogs and haven't found many of those signatures, but we also expect most of those signatures to die out on a timescale of 1 million years or so. So these might just be things that merged, 50 million years ago, and so we don't see any evidence other than this asteroseismic evidence. So the number of stars here, this is about 1% of the sample that we've identified. That's about what we'd expect. So it turns out something like a few percent of these should merge kind of near the end of the main sequence or at the base of the red giant branch where these stars live. So it's maybe a little bit less than we expected to find, but it's roughly consistent with the expectations. So I think that's a really nice, it's one of the really nice tools we've been able to develop from asteroseismology. Not just understanding normal stars, but also finding all the interesting exceptions, magnetic stars, binaries, and those kinds of things. So, another thing we can do with these red giants, if you zoom in on one of those power spectra, so now what I'm showing here is a zoom in. So these are these gravity modes I've been talking about. They have this kind of constant spacing here. If you look in, each one of those gravity modes is actually a triplet. So these are L equal 1 gravity modes inside of the star. So their angular structure is an L equal 1 spherical harmonic. But if you remember from quantum mechanics, for L equal 1 spherical harmonic, you have m equal -1, 0, or 1. So those basically correspond to modes that propagate with the rotation of the star, against it, or orthogonal to it. And so these modes are split into triplets basically by the rotation rate of the star. But it's a little more complicated than that because stars, not all of the star has to rotate at the same rate, right? The core could rotate faster than the surface. So what you actually get is some weighted average of the internal rotation rate of the star. And so this mode right here, this is a mode that's a mixed mode. It has some of its energy in the core of the star and some in the surface, and so you can see the rotational splitting here. This mode is a gravity-dominated mode, so it has more energy in the core. That means it's more sensitive to the core rotation. And you can see that the rotational splitting here is larger for this mode than it is for this one. So that's telling us that the core rotation rate is faster than the surface. And in fact, when you make these measurements for most stars, what you basically get is a core rotation rate measurement, not the surface. That's what you're most sensitive to. So this measurement has now been made for hundreds of stars. And this is super useful because it allows us to understand the process of angular momentum transport inside of stars, which is one of the big unsolved problems with stars. So as stars evolve, their cores tend to contract, their envelopes tend to expand. So if each layer conserved angular momentum, the outer layers would be spinning very slowly, and the core would be spinning very rapidly. But of course, if there's any friction inside of the star, any angular momentum transport, that's going to tend to slow down the core and spin up the envelope. And that process we really don't understand. But that's super important if you want to understand things like the spin rates of white dwarfs, which form out of these cores, or the spin rates of neutron stars or black holes that form out of these cores. You need to understand this angular momentum transport question. So that's what we've tried to do, and this is some work with Tony Pyro, Adam Germain, and Lin Hao. trying to interpret these measurements and build a theory that explains the asteroseismic rotation rates that we've been able to measure. So to put those measurements into context, this is a plot from Matteo Cantiello's paper several years ago. These were the core rotation rates measured at the time of red giant branch stars. They're typically of order 10 days is the core spin period. All these lines are predictions from stellar models. And what you can see right away is none of the models go through the data, right? So none of these are working. The purple and green lines, these are models where basically the only angular momentum transport mechanisms were some hydrodynamic instabilities and things that people had tried to build models for and put into stellar models. So these hydrodynamic angular momentum transport mechanisms are pretty hopeless. They predict rotation rates that are 100 or 1,000 times too fast relative to what we observe. So clearly, the frictional processes are quite important. Angular momentum transport is much more efficient than what most models had predicted. The best, or the closest model that came to the data was this red line, and this is the prediction from what's known as the Taylor-Spruit dynamo. And that is a magnetic angular momentum transport mechanism. And the idea there is that anytime you have a magnetic field and you have differential rotation, you tend to stretch the field lines. So a good example, you can think of this as being a magnetic field line, and differential rotation in the star will tend to twist it up. So we're building a toroidal field due to the more rapid rotation in the core. And eventually, if you twist the field line too much, it's going to tend to kink and buckle and squirt out to the side. So this is a classic kink instability of magnetic fields. And the same thing can happen in stars, and that's called the Taylor instability. And so that happens once the field has been amplified strong enough. And basically, that's inevitable. So even if you have a very weak radial magnetic field and you have differential rotation, what that means is Q omega here, this is basically the level of shear within the star. And the azimuthal field, or the toroidal field, just builds up linearly with time due to the differential rotation stretching out the radial field into a horizontal field. And eventually that horizontal field will become unstable. So this is the Taylor instability, and there's a seminal paper by Hank Spruitt trying to model what happens, what's the nonlinear evolution of this instability. What actually happens? Is there a magnetic dynamo that results, and how does that produce angular momentum transport? So the idea is that this toroidal field, these field loops, basically slip sideways. It's an m=1 instability. So we have some work in prep where we've actually managed to simulate this. This is a three-dimensional simulation with Daedalus done by Suo-Ching Ji, who was here a couple years ago. And this shows kind of the nonlinear turbulent saturation of this instability, which we're still trying to understand. We think what's actually happening here is that you basically have a secondary shear instability that saturates this instability. But we don't totally understand it yet. It's a pretty complicated process. But we're starting to be able to simulate these things. But we can also make some progress analytically, I think. And so the picture here for how this instability saturates is that the linear growth rate scales basically like the alpha and frequency, which is like the magnetic field. It scales like that field strength squared. And eventually, once this instability gets stronger and stronger, there will be some nonlinear damping that damps the instability and saturates the magnetic field strength that we get out of it. So we can match the energy input into the magnetic field due to this differential rotation, that's what this term is here, with some damping of the field energy due to this instability. And you can put all these elements together and get a prediction for what is the magnetic torque that's actually exerted. If you calculate BR phi, that's a magnetic torque. You can translate that into an effective viscosity that's trying to damp out this differential rotation inside of the star. So the prediction from this work is that it should scale like rotation rate divided by Brunt-Väisälä frequency. It's that same buoyancy frequency. It should scale like that to the fourth power. The problem is that this ratio in real stars is very small. So you raise it to the fourth power, you get very weak angular momentum transport. So in some of the work I've done, the part of this process that we question is whether or not we really damp energy at this rate. So the idea here is that we're actually damping the energy in this large-scale ordered toroidal magnetic field. And that's hard to do, right? If you have an ordered magnetic field, it's hard to dissipate all that energy because you can't make the magnetic field lines reconnect very well. What you tend to dissipate is the disordered part of the field. So if your magnetic field kinks sideways, then, like we saw in the demonstration, when it kinks to the side, then it can start to intersect with itself and reconnect. And so that's the part of the magnetic field that we think is actually dissipated in this process. So we go through some analytic arguments saying the main difference here is basically that only this kind of only the energy in the perturbed magnetic field is damped out. That's a smaller amount of energy, and so that means that the instability can rise to a larger amplitude, build up more energy in the magnetic field before it saturates, and that will give you a stronger magnetic torque. So when you put all these equations together, you get the same result as before, basically. It's just that now it scales like rotation rate divided by Brunt by Solid frequency squared. So we get much stronger torques from this mechanism. So that's the idea. So we can put both of these models into stars, and into stellar models, and see which ones agree with the data. So that's what we've done here. So these lines are predictions for what the core rotation period should be for stars evolving along the red giant phase as a function of time. So the core rotation period, according to the classic Taylor-Spruitt model, is this black line. You can see that that's predicting rotation periods that are too fast by about a factor of 10, basically at all these different phases of evolution. So these are typical red giant core rotation periods. These are core rotation periods during the clump, which are about 100 days, and then white dwarfs typically rotate at a couple days. You can see that this new prescription does a much better job of matching the data all through these evolutionary phases. So it doesn't prove that this model is right, but we at least have a model now that is consistent with the data. So what's happening here basically is that on the main sequence, the core and the envelope rotation period is this blue line. They're basically the same. So stars on the main sequence should be roughly rigidly rotating, which is what we typically observe in most stars. But then, kind of at the start of the red giant branch, the core decouples and starts spinning much faster. And that's due to the buildup of this strong density gradient in the core. That gives us a large Brunt by Solid frequency and a small amount of angular momentum transport. So you get this decoupling. Right here, what actually happens is the core ignites helium in its core. And so then it expands, and because it expands, it has to spin down. And then the core contracts into a white dwarf after it's burned all its helium, and it spins up again. So that's the basic idea. So this matches the data we have. Unfortunately, we don't have much data for high-mass stars. They basically, their structures are not favorable for these asteroseismic measurements, and also they're much rarer, so we just don't have core rotation rate measurements for them, at least in the post-main sequence. But we can take the same prescription and put it into models of massive stars and see what it predicts. So that's what Lin Hao and I did several years ago now. And so what's plotted here is this is the angular momentum content in the helium core of a star as it's evolving as a function of time. So each of these lines is a different mass. And what you can see here is that the core starts out with a lot of angular momentum on the main sequence, and then it just goes off this cliff. And so what's happening here is the star is moving from the main sequence and it's turning into a red supergiant. So its envelope is expanding and spinning down. Its core is trying to contract and spin up, but because of this angular momentum transport, it's losing all of its angular momentum into the surface layers of the star. So according to these models, it loses about 99% of its angular momentum right after the main sequence, continues to lose angular momentum as it evolves, and the end of these tracks is when the core collapses into a neutron star. So we can predict, since we know the angular momentum in this core, we can predict the approximate neutron star rotation rate if we just assume that that angular momentum is conserved during the explosion process. Probably not a perfect assumption, but it should give us some prediction of rotation periods to expect for neutron stars. What you can see here is we predict those rotation periods are typically about 100 milliseconds. So that's actually pretty compatible with typical young pulsars. They typically spin at periods of about 100 milliseconds. Some are faster, some are slower. But this is the right order of magnitude. So it's at least to first order, this theory is compatible with neutron stars and pulsars as well. Okay, so we can make the same prediction for black holes. So again, these are the same types of models, and now what we're assuming is that all the mass and all the angular momentum in the helium core falls into the black hole. And we can predict in that scenario the effective spin of the black hole that you should form. So all these black dots, these are predictions from single star models. And what you can see is that the prediction is basically almost zero spin, is what we expect. Basically, all the angular momentum gets sucked out of the core, and so very little falls into the black hole. The gray points, these are measurements from LIGO, which have large uncertainties. Actually, we have a lot more of these now. This isn't the most up-to-date plot. So they have large uncertainties, but what you can see is typically they're close to zero. There's not many. What we really measure is this chi-f, which is like a weighted average of the spins of both black holes, but they're close to zero for the most part. And so there's a lot of analysis and a lot of debate about exactly how small these spins are. But they're close to zero. There are some that are spinning faster, and there's definitely a skew where there's more positively spinning black holes than negative. That would mean that their spin is in the same direction as the orbit when they merge, which is what we expect from most binary star models. So there are some models, like this green circle and this yellow one, that do predict much larger spin. And these are binary star models, where you actually have two helium stars, or it could be a black hole and a helium star, that are in an orbit of maybe a day or so. And so then you can tidally spin up that helium star, just like I've been talking about other forms of tidal dissipation. If you spin up that helium star during that phase, you can basically rejuvenate all of its angular momentum. And that gives you models like this green one right here. And of course, all the mergers that we actually observe between black holes, those are binary black holes, right? So if they form from binary, from stars, they probably form from binary stars or in dense clusters. But if they form from binary stars, we expect these tidal processes to occur. So I'll come back to the predictions for that in a second. So what we've done is, in this paper with Wenbin just last year, is we ran a bunch of models of these binary stars accounting for this tidal spin-up. So that rejuvenates the core angular momentum. So now, again, I'm predicting the neutron star rotation period. Now I'm predicting it as a function of the mass of the star that collapses. So all these red points, these are wide binaries where there's no tidal spin-up. And so again, we're predicting neutron star rotation periods. This model is slightly different, so it's more like 50 milliseconds instead of 100. But if you put those stars in a tight binary, then you get faster neutron star spin. So, these blue points at the bottom, these are binaries with orbital periods of a few hours. And you also predict from these models that you get faster spin for higher mass progenitors. And the reason behind that is that these high mass stars, in the late phases of their evolution, they burn through all their heavy elements very quickly. So in these low mass stars, it might take them 1,000 years to go through carbon burning. These high mass stars might do it in like a year or less. So there's just not enough time to suck out the angular momentum of the core as it's collapsing. And so you get much faster neutron star rotation periods, according to these models, down into the millisecond regime. And these are the kinds of rotation rates that we think are capable of powering energetic transients like superluminous supernovae, broadline 1C supernovae, and gamma ray bursts. So there's been a lot of literature on powering superluminous type 1C supernovae with rapidly rotating magnetars. We think we can do it, but only with fairly massive stars that are in tight binaries. So interestingly, there have been some efforts, all these green stars are from a paper by Blanchard et al., trying to measure what the magnetar rotation rate would have to be and what the ejecta of these type 1C superluminous supernovae are. And they indeed find a correlation between the ejecta mass and the rotation rate that's similar to the correlation we predict. It is offset. So it's not clear if the models are predicting too slow of rotation Another possibility is that these ejecta-mass measurements, which are very difficult, are biased too low. So it's not clear, but we get the same correlation. So that's very interesting, both for the prospect of these kinds of stars explaining these type 1c superluminous supernovae, but also just for testing these angular momentum transport models. So going back to black holes, again, if you tidally spin up a helium star, give it a lot more angular momentum, so when it collapses into a black hole, you can get much more rapid spin. So these red circles and squares, these are basically binary models with a large orbital period, no tidal spin up, slowly spinning black hole. These models predict less than 0.1, so that's very small. Whereas if these black holes are in a tight binary, you can get spins of order unity. So we expect to see both in LIGO. We expect to see a lot of very slowly rotating black holes that were born in slightly wider period binaries, and at least a few, some fraction of highly spinning black holes that were formed in these tight binaries. So I think 04 is going to start when? What's the latest prediction? Sometime this year, hopefully? Very soon. 04 will hopefully start and be able to measure even more of these black hole spins to really figure out how slowly are they spinning, how many of these rapidly spinning black holes are there, and test some of these models. So that's something I'm really looking forward to. Okay, I think I'm out of time, so I will leave up my conclusions and take questions. Thank you. Mm-hmm.
Where you've got, fairly large radius and fairly large fraction of the mass. Is that consistent with what people are expecting to be the core out of which Saturn actually formed, or is some evolution of that?
Yeah, so there's been a lot of work on that from different angles, and especially people doing formation models of giant planets. One of the popular models now is this pebble accretion, where you're kind of gradually accreting pebbles at the same time that you're accreting gas. And those models naturally predict kind of this gradual transition from a icy core to this gaseous envelope. So the models often do predict that the planet should be born with these gradual transitions that can extend out this far. The question is whether or not those are preserved over time or not. In this model, the data clearly shows that we do have those gradual transitions. So it's possible that could happen through some other mechanism after formation, but I think it would be consistent with those kinds of formation models.
So Jim, can you put 1 BC plot?
Yeah.
This went too fast.
Yeah, a little fast at the end. Okay.
Yeah, this one.
This one?
Yeah.
Okay.
The usual story for 1 BCs is a little quite complex, as you know. There's supposed to be very large amount of mass transfer.
Yes.
And so that's one. And the other one is there's variable mass loss, which could in fact be, one effect could in fact be, not very smooth.
Yep, that's right. So,
Whereas I got the impression that all of your model is like as though it's a single star.
no, so these are all binary models here. And these binary models are basically for one object, doesn't matter what it is, and then a helium star that's already been stripped of its hydrogen. So it would produce either a type 1b or a type 1c supernova. And these are the predictions for the neutron star spins you get from those kinds of models.
What do you assume is mass loss going to do for the helium star? And what is the initial condition for it?
So the initial condition is basically you have a helium star that was the helium core of its progenitor. The envelope gets stripped. We're kind of agnostic to how it gets stripped, but maybe a common envelope phase or stable mass transfer. So now you're left with a helium star and, say, a black hole or a neutron star or even main sequence star. But they're in this orbital period of order a day, and so that tidally spins up.
You're assuming the initial period is long.
I'm assuming the initial spin is 0, actually. The models, again, these angular momentum transport models predict you start with slow rotation. but then it's rejuvenated by the tidal spin-up of the star. And so basically, we don't get any tidal spin-up at long periods, so we get long rotation periods for the neutron stars. But you get tidal synchronization at short periods, and so then you have a lot more angular momentum.
So the point I was confused is how do you get ejecta mass of 30 from a helium star?
So this, so this is basically the mass of the envelope of this star when it collapses. These wouldn't necessarily give you a supernova. A lot of these would probably turn into black holes. But if they do explode, they would have a rapidly rotating enough neutron star to power one of these energetic transients. Now, people modeling that collapse are trying to figure out when does the star explode, when does it not explode. And it's not a monotonic function of mass. It can. People have definitely found that very massive stars can indeed explode. It depends on the density profile of the core when it collapses fairly sensitively. So that's not totally understood, but certainly some of these massive stars probably can explode. Should be rare events, but these broadline 1Cs are also, or these superluminous 1Cs are also very rare. There's actually a paper that came out on arXiv just today, basically reaching the same conclusion and showing the same correlation. They did some population modeling saying that the rates are consistent as well. So I haven't read that yet, but it's an exciting possibility. Yeah.
For hot Jupiter systems revolving under resonant mode locking, does the merger typically happen when the star is on the main sequence, or does the star just fall, become a subgiant, giant star?
I think it would. I think it would depend a bit on exactly what the orbital period was at the start. So, for instance, in this model, the planet is migrating in very slowly, and it would get tidally destroyed somewhere around here. So that might actually be after the star has evolved off the main sequence. But if I started it a little bit higher, it would survive, basically. Or if I started a little lower, it would get destroyed earlier. So I think both can happen.
Sort of like keep switching back to your other plot with the 1BC.
Yeah.
I can imagine there'd also be some uncertainties in measuring the rotation periods of these systems.
Oh, yeah.
But are there any possible measurements of ejecta masses in galactic supernovae hosting pulsars?
Good question. There probably are. I think it's a hard measurement. I don't know a lot about it. The other thing is, these superluminous 1Cs, this is like less than 1 in 1,000 supernovae. So the chances that a remnant we see in the Milky Way is one of these is very unlikely.
I'm thinking of the lower mass.
Yeah, so for the lower mass, I didn't talk about these purple and black points. These are some other supernovae, kind of more ordinary 1BCs where people have tried to make these same kinds of fits to the light curves and tried to infer the ejecta mass and neutron's magnetar rotation period. And those are kind of consistent with these lower mass, more moderately rotating stars. But I should say that inferring these periods is, right, you're just fitting some magnetar model to the photometry. It's very uncertain, I think.